Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at the group 17 elements, the halogens. We're going to talk about how their boiling points, electronegativities and reactivities change down the group, their abilities to act as oxidizing agents, the ability of halide ions to act as reducing agents, and how to test for halide ions in solution using aqueous silver nitrate and ammonia. Before we talk in detail about the halogens, there are a couple of essential ideas you need to be comfortable with. Electronegativity describes the power or ability of an atom to attract the pair of electrons in a covalent bond towards itself. The higher the electronegativity of an element, the more its atoms are able to attract electrons in a bond towards themselves. Oxidation refers to the loss of electrons by a species, and reduction, the gain of electrons by a species. Recap done? Let's go! The halogens are elements in group 17, or 7, in the periodic table, and are fluorine, chlorine, bromine, and iodine. Astatine is technically a halogen, however it's very unstable and a radioactive element, meaning we don't really consider it when discussing the halogens in chemistry, as it's too unstable to form any compounds that can be studied. The halogens exist as diatomic molecules when in their elemental form, with the formula X2. They are nonpolar molecules, and within a sample of the halogen, molecules experience weak temporary instantaneous dipole-dipole interactions, also called London dispersion forces. As atoms of the halogens get larger as you go down the group, the molecules they form also get larger, meaning stronger temporary instantaneous dipole-dipole interactions between them, and higher boiling points. Boiling points increase down the group. For example, fluorine, F2, has a boiling point of minus 188 degrees Celsius, chlorine, Cl2, minus 35 degrees Celsius, bromine, Br2, positive 59 degrees Celsius, and iodine, I2, positive 184 degrees Celsius. A clear increase in boiling point as we go down the group. The increased size of the atom down the group doesn't just affect the boiling points of their molecules, however. The electronegativity of the halogens decreases as you go down the group. This is because as the atoms get larger and their atomic radius increases, electron pairs in a covalent bond to the atom are further away from the nucleus of the atom, and this means there is less attraction between the bonding electrons and the nucleus. We can see this when we look at the pooling electronegativity values for the halogens. Fluorine, the top of the group, has a value of 4.0, the highest of any element in the periodic table. Chlorine 3.0, bromine 2.8, and iodine 2.5. This results in bonds made to larger halogen atoms being less polar as you move down the group, such as carbon-halogen bonds. Carbon-fluorine bonds are more polar than carbon-chlorine bonds, carbon-chlorine bonds are more polar than carbon-bromine bonds, and so on. In fact, carbon and iodine have such similar electronegativities, both 2.5 on the pooling scale, that carbon-iodine bonds are considered nonpolar. As halogen atoms have electron configurations of p5 in their outer shells, when they react they usually gain one electron and form negatively charged ions, which have an electron configuration of p6 in their outer shells, and a charge of 1-. These negatively charged ions are called halide ions. For example, fluorine atoms form fluoride ions, F-, chlorine atoms form chloride ions, Cl-, bromine atoms form bromide ions, Br-, and iodine atoms form iodide ions, I-. Due to the halogens getting larger as you go down the group, their ability to attract and gain electrons decreases. This means the general reactivity of the halogens decreases down the group. The reason behind this is similar to the explanation for the trend in electronegativity down the group. Larger atoms have more inner electron shells, meaning outer electron shells are repelled further away from the nucleus by these inner electron shells, and as a result experience a weaker force of attraction to the positively charged nucleus. This is referred to as inner electron shielding. We can see this trend in reactivity with reactions between the halogen atoms and halide ions of different halogens. More reactive halogen atoms are able to force the halide ions of less reactive halogens to give up their extra electron and become halogen molecules again. This is referred to as a displacement reaction, and the more reactive element is said to displace the less reactive element. We can take this one step further and describe the halogens as reacting as oxidizing agents. An oxidizing agent is something that takes electrons from another species in a reaction and causes that species to be oxidized, lose electrons. I know it sounds a bit confusing, but an oxidizing agent gets reduced itself and causes something else to be oxidized. The ability of halogens to act as oxidizing agents decreases down the group. The more reactive the halogen, the better it can attract and hold on to an extra electron, compared to a less reactive halogen. If a halide ion comes into contact with an atom of a more reactive halogen, the more reactive halogen is able to attract the extra electron and pull it away from the halide ion. The original halide ion then becomes a halogen again, and the more reactive halogen atom becomes a negatively charged halide ion. It's like a competition for the electron. The more reactive halogen will always win and take the electron from the less reactive halogen. For example, fluorine is the most reactive halogen, meaning if fluorine molecules are mixed with halide ions of any of the other halogens, chloride, bromide or iodide, the fluorine atoms are able to pull away the extra electron the halide ions have and gain it themselves, becoming fluoride ions with a 1- charge. They are reduced here by gaining an electron. The chloride, bromide or iodide ions become neutral atoms again, forming their halogen molecules, Cl2, Br2 or I2. As each halide ion is losing an electron, they are oxidized. Iodine is the least reactive halogen, and if iodine is mixed with halide ions of the other halogens, nothing happens. The iodine atoms are unable to pull the extra electrons away from any of the other halide ions. Chlorine is unable to react with fluoride ions, but is able to react with bromide and iodide ions, oxidizing them both and becoming chloride ions in the process. Bromine is unable to react with fluoride and chloride ions, however is able to react with iodide ions and oxidize them. This can be considered the opposite way round as well. If halogen atoms can act as oxidizing agents, halide ions can act as reducing agents. A reducing agent gets oxidized in a reaction by having electrons pulled away from it by something else that gets reduced. The ability of halide ions to act as reducing agents increases down the group. As halide ions are less able to hold on to the extra electron as you go down the group, they more easily lose them in reactions and are therefore better reducing agents. Common examples used to show this trend are the reactions of sodium halide salts with concentrated sulfuric acid, H2SO4. The sulfur in the sulfuric acid can be reduced if it comes into contact with a powerful enough reducing agent. Chloride ions from sodium chloride, NaCl, are unable to reduce the sulfur. In the reaction, sodium hydrogen sulfate, NaHSO4, gets formed, and this contains sulfur with an oxidation state of +6. As the oxidation state of the sulfur in the original H2SO4 was also +6, it remains unchanged, meaning no reduction of the sulfur. Bromide ions from sodium bromide, NaBr, are able to reduce the sulfur from a +6 oxidation state to +4, forming sulfur dioxide, SO2. Iodide ions from sodium iodide, Ni, are able to reduce the sulfur from a positive 6 oxidation state all the way to negative 2 in hydrogen sulfide, H2S. Again, the reaction has to occur in steps, with sulfur dioxide, SO2, being formed, as with bromide ions. However, this time the SO2 can go on to react with hydrogen iodide to form H2S. This nicely highlights the trend in reducing ability of the halide ions, increasing down the group, and is often a requirement of most exam boards at this level. As a final point, aqueous halide ions, chloride, bromide and iodide, can be identified using their reactions with aqueous silver nitrate followed by ammonia solution. Nitric acid is added to a sample solution followed by aqueous silver nitrate solution. If any of the three halide ions are present in the sample solution, insoluble silver halide precipitates get formed. If chloride, Cl- ions are present, a white precipitate of silver chloride, AgCl, gets formed. If bromide, Br- ions are present, a cream precipitate of silver bromide, AgBr, gets formed. And if iodide, I- ions are present, a yellow precipitate of silver iodide, AgI, gets formed. The precipitates can be difficult to distinguish as the colours of each can look really quite similar. To get around this, dilute and concentrated ammonia solutions are added. Silver chloride, AgCl, dissolves when dilute ammonia solution is added. Silver bromide, AgBr, doesn't dissolve if dilute ammonia solution is added, however will dissolve if concentrated ammonia is added. Silver iodide, AgI, won't dissolve in either dilute or concentrated ammonia solution. Nitric acid is added before the silver nitrate solution at the start to react with any other anions present that may cause precipitates to form with silver ions. For example, if any carbonate ions were in the sample solution, they would react with the silver to form silver carbonate, also a white precipitate. By adding the nitric acid first, however, any carbonate ions present react with the nitric acid, forming carbon dioxide and water. This means when the silver nitrate solution gets added, silver carbonate can no longer form, and any precipitates that do form will be from the halide ions reacting with the silver nitrate. So, to summarise, boiling point increases for halogens down the group. This is because as the molecules get larger down the group, the strength of temporary instantaneous dipole-dipole interactions, or London dispersion forces, between the molecules get stronger and more energy is required to overcome them. The electronegativity of the halogens decreases down the group. This is because as the atoms get larger, there is a greater level of inner electron shielding, meaning electrons at the surface of the atom are less attracted to the nucleus, decreasing the atom's ability to attract a pair of electrons in a covalent bond towards itself. The reactivity of the halogens decreases down the group. This is because the halogens react by gaining an electron to form ions with a 1 negative charge. And the increased level of inner electron shielding as you go down the group means it gets harder for the atom to attract an electron and form an ion, meaning the atoms become less reactive. The ability of halogens to act as oxidizing agents decreases down the group. An oxidizing agent is something that causes another species to be oxidized by gaining electrons itself. As it gets harder for the atoms to gain electrons as you go down the group, it means they are less able to oxidize something else, meaning they become weaker oxidizing agents. The ability of halide ions to act as reducing agents increases down the group. A reducing agent is something that causes another species to be reduced by losing electrons itself. As halogen atoms attract electrons less easily down the group, halide ions formed by them then are less able to hold on to their gained electron and lose them more easily, enabling something else to be reduced, making them stronger reducing agents. Chloride, bromide and iodide ions in aqueous solution can be identified using acidified silver nitrate solution and ammonia. As they form insoluble silver halide precipitates when mixed with silver ions in water, and the precipitates have different colours: white for silver chloride, AgCl, cream for silver bromide, AgBr, and yellow for silver iodide, AgI. The colours of the precipitates can be difficult to see and can be further identified by adding ammonia solution, as each has a different solubility in ammonia. Silver chloride dissolves in dilute ammonia, silver bromide will only dissolve in concentrated ammonia, and silver iodide won't dissolve in either dilute or concentrated ammonia. The silver nitrate used must be acidified by adding acid first to ensure that any other anions present that may cause precipitates to form, such as carbonate ions, are reacted and removed from the solution. I hope you found this video helpful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.